Okay, so boiling points and freezing points, I'm going to do these together because we'll use the same types of equations and we can show this on a phase diagram, which is pretty cool. So for boiling and freezing points, because the presence of a solute lowers the vapor pressure, the solution has to be heated to a higher temperature for the vapor pressure to equal the external pressure. So that's kind of the step-by-step logic for getting you to the boiling point change. And so let's show this on a phase diagram. So I'm going to put the phase diagram for water on here. Um, right, pressure versus temperature. At 1 atmosphere, I've got my normal freezing point and my normal boiling point marked. By lowering the vapor pressure of the solution, what this really does is that it lowers my solid liquid and liquid vapor lines on the phase diagram. So my triple point gets lowered, and then right, I've got these new lines drawn. They're just lower on the diagram than they were for the pure solvent. So I've got pure solvent in black, solution in blue, and if you look where 1 atmosphere crosses these two lines, I'm going to start over at the right with the boiling point. At 1 atmosphere, when I drop down to look at the temperature that the solution would boil at 1 atmosphere, the boiling temperature is now higher. So I had the boiling temperature of the pure substance. I've got that marked as a TB with a little 0 for the pure. And then the boiling temperature of the solution, there's some change that happened because I dissolved stuff in it. And you see the same thing for the freezing point, but it's going in the opposite direction, right? So for freezing, we're trying to organize all of these solvent pieces. The solute that we have in there disrupts the ability to organize those. So we have to go to a colder temperature to get it to finally turn into a solid at whatever pressure we're looking at. So my freezing point gets lowered, my boiling point gets raised. I have a delta freezing temperature and a delta boiling temperature. I have an equation for each of these. So the way that this equation is given is that it's a calculation of the delta. So delta TB is equal to I KB times the molality of the solute, and then delta TF equals I KF times the molality of the solute. So KB and KF are boiling point constant and freezing point constant. This depends on the solvent. So these are values that you would have to be given or that you could go look up, but it's for the solvent. So water has a unique KB and KF value. What the solute does, the way that the solute gets included in this calculation is with the Van't Hoff I factor. So we didn't explicitly put it in the vapor pressure calculation, but it does show up here. Now, also, this is just calculating the delta. You do still then have to take the original boiling temperature and add the delta to it, or take the original freezing temperature and subtract the delta from it. As usual, let's look at some examples. So we're going to look at a solution prepared by dissolving 1.7 moles of ethylene glycol in 1 liter of water. And we have the density for water. We need to calculate its new boiling and freezing points. And we have the KB for water and the KF for water. So you can see this is degrees Celsius per molal or per molality. Not sure the right way to say that, but if we're taking that constant times the molality, then we just get a delta in degrees Celsius out of this, which is the same as a delta in Kelvin. So it doesn't matter what temperature we need to report it in, we'll have an appropriate delta for that. Okay, so molality of the solution, we need moles of solute per kilogram of solvent. We're given the moles of solute, so it's 1.7 moles of ethylene glycol. And we're given the volume of the solution, but this is in grams per mil. So 1 liter is 1,000 mils. If I convert that to grams, that's 1,000 grams. And if I convert 1,000 grams to kilograms, that's 1 kilogram. So I have 1 kilogram of solvent, 1.7 moles of the solute. So this is a 1.7 molality solution. The I factor, so ethylene glycol, this is something that's a non-electrolyte. You know that it goes into solution just because I'm telling you we're preparing a solution with it. And you know that it's a non-electrolyte because it doesn't look like the name of any of the ionic compounds that we've ever talked about. So the change in boiling temperature, my Van't Hoff I factor is 1 because it's a non-electrolyte. I have my constant, which is 0.512 degrees C per molality, and the molality is 1.7. So my delta TB is 0.87 degrees Celsius. So my new boiling temperature is whatever it was before, which was 100 since my solvent is water, plus that 0.87. So my new boiling temperature is 100.87 degrees Celsius. The freezing temperature, calculated the same way, 1.86 degrees Celsius per molal, 1.7 molal solution. This gives me a delta TF of 3.2 degrees Celsius. So my freezing temperature is wherever I started minus the delta. So 0 degrees minus 3.2. My new freezing temperature is negative 3.2 degrees Celsius.